Okay, start that. Come here. Okay, SSTables. Maybe we start with the cards today. Let's see. MapReduce is a programming paradigm to handle queries for distributed tables. Large amount of data in bulk across many machines. Distributed tables. Is that wrong? No. We'll say it was good. What are the advantages of the document model? Schema flexibility, potential for hierarchical data, data locality, so you can get it all at once, no joins necessary. Schema flexibility, hierarchical data, documents, data locality. This is okay. Okay, I'll say this is finally good, right? Useful when, yeah. I'll say that was a good answer. It wasn't the best. Who is your daddy and what does he do? So what is a data model? Why is it important? How we organize our data, it's important because it defines how we're going to think and therefore solve the problems that we're faced. Data is structured, related, and manipulated. It acts as a contract between applications, influencing design, maintainability, and performance. Say that's okay. What are the key characteristics of the relational model? Joins and normalization. Tables, yeah. Structured data, so tables. This is the key part though. Uses SQL. I don't think that's, yeah. Forces normalization, yeah. And decades of tooling, whatever, we'll say that's good. When is the document model a better choice? If you need flexibility, a lot of these are repeated. Flexibility, when your application uses single objects, or when the data is represented by a document. And you can also, you won't incur too much duplication cost. Or duplication won't be a big factor for you. Can be tolerated, that's what I'm trying to say. Cool. Yeah, yeah. Read as a whole, yeah, good. Nice. Okay, so SSTables, let's reread some of this. If you keep things tidily ordered, you're just too lazy to go searching. A database does two things. It stores and retrieves data. You should care how the database does things because you'll need an engine that is suitable for your application. Given a workload, certain engines will perform differently. Choosing the correct one is crucial. Specifically in this book, logs are append-only files that are not necessarily human readable and could be just for other programs. Yeah. Indexes speed up reads, but they incur overhead, so they're left up to the application developer to make sure not as little overhead as possible is incurred. Hash indexes. Using a dictionary or a map that most languages have as an example, one could create indexes using native functions, the desired key, and byte offsets. of where on disk to find the data. Compactions create segments. Segments can then be merged. By doing all this in the background, we can serve reads from the old files and serve writes to the new files. Once compaction and merging is complete, we delete the old file. That's right. So compaction and merging. Yeah, we're doing compaction, and this is specifically for hash indexes or write-only log files. And what we're doing is getting rid of, because of the mechanism, not the mechanism, the approach to a write-only log file would be you always update. So you'll end up with duplicate rows with outdated data. Compaction removes the duplication in that log file to reduce the size. And merging, because you could end up with one file that's very large and after compaction it's very small. And if you have multiple files that are large that end up small, you can create one medium-sized file. So you don't have to go to disk as often. And there's some challenges presented with this approach. And it's kind of like I can't remember. File format, deleting records, you have to have tombstones, crash recovery. Oh, these are things also for just hash indexes, not necessarily compaction merging. Partially written records, yeah, okay. Tombstones is how we manage deletions, and then while append-only indexes might not seem intuitive at first, it solves random writes, crash recovery, and data file fragmentation. Okay. Cool. Okay, so SSTables and LSM trees. Okay, so we have a section. Each log structured storage segment is a sequence of key value pairs. These pairs appear in the order that they were written, and values later in the log take precedence. Apart from that, the order of key value pairs in the file does not matter. Now, we can make a simple change to the format of our segment files. We require that the sequence of key value pairs is sorted by key. We call this format sorted string table, or SSTable for short. With this format, we cannot append new key value pairs to the segment immediately, since writes can occur in any order. We'll see shortly how to write SSTable segments using sequential I/O. Alright, so there's something here, right? Let's define SSTables. So if hash index was managed by a write-only file. No, I don't want to do this. SSTables. A log file So SS tables have several big advantages over log segments with hash indexes. Merging segments is simple and efficient because they're sorted. Even if the files are bigger than the available memory, the approach is like the one used in merge sort algorithm and is illustrated figure 3.4. You start reading the input files side by side, look at the first key in each file, copy the lowest key according to the sort order to the file output, and repeat. This produces a new merge segment file, also sorted by key. Sure. If the same key appears in several input segments, remember that each segment contains all the values written to the database during the period of time. This means that all the values in one input segment must be more recent than all the values in the other segment. Assuming that we always merge adjacent segments, when multiple segments contain the same key, we can keep the value from the most recent segment and discard the values in older segments. I see. So if you're going in order, if you're like sorting these things, then you would eventually all pointers would be pointing at the same key, and then at that point you would say, like, if whatever's most recent, take that one, and then advance all three. Yeah, okay. In order to find a particular key in the file, you no longer need to keep an index of all the keys in memory. See figure 3.5 for an example. Say you're looking for the key handiwork, but you don't know the exact offset of the key in the segment file. However, you do know the offsets for the keys handbag and handsome. And because of the sorting, you know that handiwork must appear between those two. This means you can jump to the offset for handbag and scan from there until you find handiwork. What is this? Oh, okay. I see. Basically, you keep bookmarks instead of an index of all keys. Like, you can get close enough. You still need an index, an in-memory index to tell you the offset of for some of the keys, but it can be sparse. One key for every few kilobytes of segment file is sufficient because a few kilobytes can be scanned very quickly. Interesting. Since read requests need to scan over several key value pairs in the requested range anyway, it is possible to group those records into a block and compress it before writing it to disk, indicated by the shaded area in figure 3.5. Each entry of the sparse in-memory index then points at the start of a compressed block. I zoned out during this. Since read requests need to scan over several key value pairs in the requested range anyway, it is possible to group those records into a block and compress it before writing it to disk. Each entry of the sparse in-memory index then points at the start of a compressed block. Besides saving disk space, compression also reduces the I/O bandwidth use. Okay. So key one. So the first one was merging. collisions, duplicate. Duplicate keys across what was the second one? Oh, we can keep bookmarks. And then, since read requests need to scan over several key value pairs in the requested range anyway, I don't really understand this point. Like, hmm. So fine so far, but how do you get your data to be sorted by key in the first place? Our incoming writes can occur in any order. Maintaining a sorted structure on disk is possible, CB trees, but maintaining it in memory is much easier. There are plenty of well-known tree data structures that you can use, such as red-black trees or AVL trees. With these data structures, you can insert keys in any order and read them back in sorted order. We can now make our storage engine work as follows. When a write comes in, add it to an in-memory balanced tree data structure, for example, a red-black tree. This in-memory tree is sometimes called a mem table. Okay. So so a mem table is an in-memory store we use a mem table for writes. Maintain sorted order. Read. We then the so I think it's like on write to mem table. Create segment file. Let's just do on read. The scheme works very well. It only suffers from one problem. If the database crashes, the most recent writes, which are in the mem table but not yet written out to disk, are lost. In order to avoid that problem, we can keep a separate log on disk to which every write is immediately appended. Just like in the previous section, that log is not in sorted order, but that doesn't matter, because its only purpose is to restore the mem table after a crash. Every time the mem table is written out to an SS table, the corresponding log can be discarded. So interesting. It never ends, bro. This log file. Okay. The algorithm described here is essentially what is used in LevelDB. and RocksDB key value storage engine libraries that are designed to be embedded into other applications. Among other things, LevelDB can be used in a RIAC as an alternative to Bitcask. Oh, used in RIAC, not a RIAC. Similar storage engines are used in Cassandra and HBase, both of which were inspired by Google's Big Table paper, which introduced the terms SSTables. So I've read the Big Table paper and I've looked at Big Table, so I think that's why a lot of this is familiar. Originally, this indexing structure was described by Patrick O'Neill et al. What does that mean? Let's just ask ChatGPT. So et al. Is short for the Latin phrase olli, I don't know, which means and others. So why would seems silly. Why would you use a different language in the middle of your sentence? Just say and others. You save. Let me see how many. 1, 2, 3, 4, 5, 6 versus 1, 2, 3, 4, 5, 6. You save 4 keystrokes by writing et al. Instead of and others. That's a pet peeve. Why would I? So why? Is it proper English to list all other people, or would just saying and others be sufficient for something like a textbook? Good question. It depends a little on the context. In formal citations, it's standard to say et al. After the first author instead of listing all the names. In regular writing, it's perfectly fine and often clear to just say and others. Are they listening to me? If you prefer English over Latin, what? And others. Okay, so it's a citation thing. That's why people use it. Still think it's stupid. Under the name log structure merge tree. Originally, this indexing structure was described by Patrick O'Neill under the name log structured merge tree, building on earlier work on log structured file systems. Storage engines that are based on this principle of merging and compacting sorted files are often called LSM storage engines. Lucene, an indexing engine for full text search used by Elasticsearch and Solr, uses a similar method for storing its term dictionary. A full text index is much more complex than a key value index, but is based on a similar idea. Given a word in a search query, find all the documents, web pages, product descriptions that mention this word. This is implemented with a key value structure where the key is a word, a term, and the value is the list of IDs of all documents that contain the word, the postings list. In Lucene, this mapping from term to postings list is kept in SSTables like sorted files, which are merged in the background as needed. Oh man, it's quite a bit. Oh, I'm tired. Okay. Let's see. Oh, this is really just informational. So LSM Tree. I don't know what I'm writing. Oh. The combination. Creates hence storage engines. I don't know. Hmm. 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 I'm just looking ahead, so I don't have a ton of time left. There's still so much here too. This chapter's so long. Like 20 pages. And like, how many pages did I just get through tonight? 3. Oh, okay. Interesting.